In this section, we're going to learn about 6 more identities. They are the sum and difference formulas for sine, cosine, and tangent, sometimes also called the addition and subtraction formulas. As you can see in these formulas, I just have the sine and cosine ones here on the first page, but we have addition and subtraction of 2 numbers or angles. Again, we can think of these as real numbers, and we can also think of them as angles. So we have a sum formula and a difference formula for each function. The tangent ones will be a little bit later here. So when you're using these, it's helpful to pay attention to the pattern, and you can see there's a clear pattern. With sine, you always take, whether it's an addition or subtraction here, the sine of the first number times the cosine of the second number. And then if it's addition, you add. If it's subtraction, you subtract. And then the cosine of the first number, sine of the second. So notice those are the same, it's just the addition and subtraction is different. And when you're doing this, rather than you think of x, y as you're trying to remember, I always think of first number, second number, or first angle, second angle. Because in the x and y don't really matter, right? They're just placeholders for whatever numbers are here. And what's more important is the order of them. Cosine sum and cosine difference. Notice in these patterns we have cosine, cosine, then sine, sine, cosine, cosine, sine, sine, and then the addition you actually subtract in the evaluation, and then in this difference formula here you add over here. So the signs there flip, and the pattern is different as well. But again, between the two cosine formulas, that's the same pattern. All right, so let's go ahead and apply these. I can't remember if I talked about proving them or not, but if you're interested in the proofs, look in the textbook. I just decided to leave that out because it's a little long. The proofs, see, we would start with proving this one, and it is a little long, so I'm just going to leave it out. The video isn't too long, and if you're interested in that, just read it in the textbook. Okay, once you get that one proved, you can prove the other 3 pretty easily. Those ones will be quicker. All right, so how do we use these? That's what we're going to focus on, using these. Well, we can use them to prove other identities. We can also use them to find exact values of numbers or angles that don't necessarily have a reference angle. That's one of our special angles. So of course 15 degrees, that is already acute, right? And it's not one of our special acute angles that we know the exact value for the 6 trig functions. So what we can do if we want to find this exactly, now of course on the calculator we can get an approximation, right? And I have my calculator here. So make sure you're in degrees. So when you do the sine of 15, you get a decimal number. But exact means we want it in, radical form. This is an irrational number, so we want this in radical form. So we can do that if we can come up with two angles. We'll say angles since this is in degrees. 2 angles who have a sum or a difference of 15 degrees. Now, for you just working with positive numbers, sum isn't going to work because our special angles would all add up to more than 15 degrees. So let's focus on a difference. So for our special angles, do we have 2 that have a difference of 15 degrees? And there's more than one way to do this. There's not just one correct answer. But I think the most obvious choice is to use 45 degrees and 30 degrees. But again, other combinations would work. So when we do this, this is our first, this is our second, we're plugging it into this pattern here. And because we know the sines and cosines of 45 and 30 degrees, we'll be able to evaluate exactly, once we plug it into the formula. So this is a difference. I should be using formula 2, right? So we take the sine of the first number, sine of 45 degrees, cosine of the second number, cosine of 30 degrees, minus cosine of the first number, cosine of 30 degrees, whoops, first number, see I already messed up, didn't I? 45 degrees. And then sine of the second number, which is 30 degrees. And each of these I know the exact value. Sine of 45 degrees is the square root of 2 over 2. Cosine of 30 degrees is the square root of 3 over 2, minus cosine of 45 degrees. Right, so these are all separate. I should point, don't evaluate them each separately. Cosine of 45 degrees is square root of 2 over 2. Sine of 30 degrees is 1/2. You don't need these parentheses here, right? But I just want to make sure we emphasize that. So this, evaluate these two products separately and find the difference. So multiply the fractions. Square root of 2 times the square root of 3 is the square root of 6. 2 times 2 is 4. Minus square root of 2 times 1 is the square root of 2. 2 times 2 is 4. Oops. And these already have a common denominator, so we can combine into one fraction, square root of 6 minus the square root of 2 all over 4. So this is the exact value. The value on your calculator is the approximate value. So if you want to check your work, you know what sine of 15 is as a decimal. You can plug this in and see if you get the same decimal. So when we take square root, whoops, gotta hit my second button there, square root of, let me turn the light off because I don't get the glare then, square root of 6 minus square root of 2, parenthesis, divided by 4, notice it's the same exact decimal number. So this is the radical representation, right, of this decimal. And when I say, so in the problems on the homework or quiz or in the worksheets, on the test, whatever, when it says exact value, we're talking about this decimal representation. They're not asking you to put the 0.2588 on your test, right? So I rounded that to 4 places. But even if I put all the decimal values down, places down, that's still an approximation because this keeps going beyond the, 9 digits the calculator gives you. Wait, 4, 8, it's 10 for this one. So keep that in mind. This is approximate. This, we can actually use an equal sign. That's exact. All right, so there's an example with using degrees. The next example uses radians. Sometimes this is harder for people. So again, we want to come up with a sum or a difference that will give us 5 pi over 12. The reference angle for this would be pi over 12, and that's obviously not a special angle. So, well, actually, sorry, the reference angle is 5 pi over 12 itself because this is already acute. I misspoke. Either way, with a denominator of 12, that's not one of the special angles, right? So we want a sum or a difference that of two of our special angles or special numbers. We don't have to think of these as angles. That gives us 5 pi over 12. Okay. So when this gets tricky because your pi over 3, your pi over 4, your pi over 6, they all have different denominators, right? So what I usually do is I don't start adding or subtracting those numbers. I look at the number here and I think about splitting it up into 2 fractions, right? And there's going to be pi on the top of both of these. And then these two numbers need to either add up to 5 or have a difference of 5. Either way, it doesn't matter. And I want them to be numbers that would go into 12 because I need to reduce 12, right? I need a denominator of 4, 3, 2, or 6. Because, we know exact values for pi over 2, pi over 6, pi over 3, and pi over 4. So I'm not going to use 1 and 4 because pi over 12 doesn't reduce. But I could use 2 and 3 because 2 pi over 12 is pi over 6 and 3 pi over 12 is pi over 4. And I know both of those exactly. So that's what I'm going to, but again, answers are definitely not unique here. You can come up with any combination that reduces. Another one, we could use 8 and 3. So let me show you. So you'd have, you know, your 12. This would have to be a difference. If you do 8 and 3, 8 pi minus 3 pi is 5 pi over 12. And then 8 pi over 12 reduces to 3 pi over 4. You can calculate that exactly. 3 pi over 12 reduces to pi over 4. You can calculate that exactly. So this would work as well. And there's many, many combinations you could come up with that would work here. Once you come up with a combination here, of course, you need to actually reduce these. So this would be pi over 6 plus pi over 4. Right, this one is, like I said, 3 pi over, wait, did I say 3 pi over 4? 2 pi over 3, I'm sorry. Good thing I went back, because I think I said 3 pi over 4 before. But that's still fine because the reference angle is pi over 3. And then this one is pi over 4. So they're, both of those you can calculate exactly, right? I'm not going to do both of these all the way through. I'm just going to do this one, but just showing you another one works. And if you go ahead and use the difference formula here and evaluate, you should get it in, you know, the same value as you do here. It might not look exactly the same. Some of these numbers have more than, well, sorry, let me think here. Right, because this one's going to have a difference and this one will have a sum, so they might not look exactly the same in terms of the numbers you're adding or subtracting, but once you evaluate them, they should be the same number. Okay, back to what we were working on. So this is a sum for cosine. Cosine pattern is to take cosine of the first, cosine of the second, and then it becomes subtraction. Sine of the first, sine of the second. Evaluate each of these. Cosine of pi over 6 is square root of 3 over 2. Cosine of pi over 2 is 0. Oh, where did I get, I felt like something was wrong. God, I'm sorry. This should be pi over 4. And then this is square root of 2 over 2. I don't know where I got pi over 2 from. Okay, so square root of 2 over 2. And then minus sine of pi over 6 is 1/2. Sine of pi over 4 is the square root of 2 over 2. And we get square root of 6 over 4 minus square root of 2 over 4. This actually is the same exact number as we got in the previous problem. Again, you can check that now when we check this. Make sure we've switched to radians. Make sure we have the right answer. Cosine of 5 pi divided by 12, the same number again. Okay, in C, this time we actually have the pattern, right? The left or the right side of the formula as written in here, and we need to evaluate it, translate it to the left side. So the pattern, we have sine, cosine, cosine, sine. That tells me it's a sine formula, and sine matches the operation, so this is a difference formula for sine. So this would be the sine of, so this is first, second, so you take the first minus the second, and notice the 80 degrees minus 50 degrees is 30 degrees, and we can calculate the sine of 30 degrees exactly. It's equal to 1/2. And of course we can't exactly calculate the sine of 80 degrees because the reference angle is 10 degrees and we don't have an exact value for that. Not memorized anyway, right? Same with the 50 degrees. Okay, here's another type of example. This time we're given the sine of alpha is 4/5. Sine of beta is -2 over the square root of 5. We're also told which quadrants alpha and beta lie in. So the information here is different than what we were given back here. Right? Here we're given the input number and we find the output. In this problem, we're given the output and we want to find some other outputs using that information. We're never actually going to find alpha and beta here. Okay, so that sometimes people read this totally wrong and they think we're taking the sine of 4/5. That's not what we're doing. We're saying the sine of alpha is 4/5. And then alpha is between pi over 2 and pi. So that means alpha is in quadrant 2. So I'm kind of in this problem, I'm building up to these two. So notice where we're going to use the sum formulas. So if we're going to use this sum formula to find the cosine of alpha plus beta, and we know the sine of alpha and we know the sine of beta, then we need to use the formula to get this in terms of alpha and beta. This is cosine alpha, cosine beta, minus sine alpha, sine beta. So see, we know the sine of alpha. This is 4/5. It's given in the problem. And we know the sine of beta. This is -2 square root of 5. It's given in the problem. Right? So you don't plug the 4/5 into the alpha because that's not, alpha is not 4/5. The sine of alpha is 4/5. This whole thing equals 4/5. This whole thing, sine of beta, equals -2 over the square root of 5. Students mess that up all the time. That's why I'm emphasizing it. Don't put 4/5 in the alpha spot. Okay, so we know we can calculate this term, but we don't know this term. So that's why I have these two. We're going to find those here. When we get those, we can just plug them in. So this cosine of alpha, we need to use the fact that the sine of alpha is 4/5 and alpha is in quadrant 2. It's important to draw this in standard position, and remember that cosine is negative in quadrant 2. So sine of alpha is 4/5. That is opposite over hypotenuse, which means the adjacent side would need to be 3. This is a 3, 4, 5 triangle. You can put a negative there if you want because you're going back 3 up 4, right? So cosine of alpha is -3/5. Don't forget the sine. Not everything is acute, right? Alpha is not an acute angle. So now we know the cosine of alpha. We just need the cosine of beta, and that's for part B. So this time we know the sine of beta. Notice beta is between pi and 3 pi over 2. So that's quadrant 3. So when I draw my triangle in standard position, I'm going to draw it in quadrant 3. Always draw your reference angle to the x-axis. I noticed in your homework some of you are drawing it to y. Doesn't make sense. No, it's always the acute angle made with the x-axis. So the height of your triangle should always be parallel to the y-axis. Okay, so there's our right triangle. Beta is actually this larger angle. This angle in the acute triangle is the reference angle. So the sine of beta is -2 over the square root of 5. Sine is opposite over hypotenuse, so the -2 and the hypotenuse is the square root of 5. So here I'll use the like here I didn't use the Pythagorean theorem. You can verify if you want, but we should. I think most of us are familiar with 3, 4, 5 triangle. But this with the radical, let's use Pythagorean theorem. So -2 squared plus, I'll call this b squared should equal the square root of 5 squared. So that implies 4 plus b squared equals 5, which implies b equals 1, or b squared equals 1, which implies b equals, it'll be -1 if you want to assign the correct sign for the quadrant, but technically if you're thinking of a length, it's just 1, right? So the cosine of beta is also a number, it's -1 over the square root of 5. And I gave this in non-rationalized form just because it's easier to, it actually makes the problem easier for you because you can just do opposite over hypotenuse. Like if we rationalize this, -2 square root of 5 over 5, then it's, I mean, obviously you can still do it, but squaring the -2 square root of 5 is a little messier. So that's just making the problem a little easier with the calculations. But in here, you may want to rationalize it. You don't have to. So now let me plug everything in. Cosine of alpha is -3 over the square root of 5. Cosine of beta is -1 over, whoopsie, I said that wrong, -3 over 5, and this is -1 over the square root of 5. Whoopsie, you can tell I'm a mom. Sine of alpha is 4/5, and then sine of beta is -2 over the square root of 5. So if you don't rationalize, these will still end up with the same denominator. If you rationalize, you'll just make sure you rationalize both, and you'll still have a common denominator. I'm just going to leave them. So this is 3 over 5 radical 5 plus, because a minus and a minus will become plus, right? And this was a negative and a negative became plus also. So those become plus, and then 8 over 5 radical 5. So this is 11 over 5 radical 5. So and if you like it rationalized, you can wait and rationalize it in the end if you want. That would be 11 radical 5 over 25. But I would take both of those answers. Now these ones we can't check like the last ones because we don't know what alpha and beta actually equal. So, you know, we'll just be careful with your work. You can find alpha and beta using inverse trig functions, but it gets tricky because remember these, like this is in quadrant 3, so you can't just use sine inverse because the sine inverse from your calculator will be the answer in quadrant 2, the negative angle in quadrant 2. So that just is making the problem harder than it really needs to be. You have to be careful there. All right, so we did cosine of alpha plus beta. We've done almost all the work now. Sine of alpha plus beta will be easy. So this is sine alpha, cosine beta, plus cosine alpha, sine beta. Sine alpha, we were given in the problem. That's 4/5. Cosine beta, we found in part B, that's -1 over the square root of 5, plus cosine alpha we found in part A, that's -3/5, and then sine beta was given -2 over the square root of 5. So this is very similar to part C, just using the other formula, of course. And we get -4 over 5 radical 5 plus 6 over 5 radical 5. Whoops, let me move up here. And this adds up to 2 over 5 radical 5. Again, you can leave it or you can rationalize 2 radical 5 over 25. Both of those are fine. Okay, so that type of problem, definitely know how to do that on the midterm. Any of these you should be able to do on the midterm. All right, here's a even harder problem because we have inverse function notation, and this is always a challenge for a lot of people. So when you use inverse notation, remember these stand for, let's just call them angles, although they can just be real numbers also. So this here, if we go back to our formula, this is like our x and our y already. Call this x and this y. So let's let x equal cosine inverse of 1/2, and y is equal to the sine inverse of 3/5. So in the first one, it's really easy because 1/2 is an output for a special angle. You can evaluate that and get pi over 3. The second one is not so easy because 3/5 isn't an output for one of our special angles. So how are we going to use this? How are we going to figure this out? Well, let's go back to this before we worry too much about this. So I'm just going to call this x and this y. So sine of x plus y from our identity is sine x cosine y plus cosine x sine y. All right, so the ones with the x are easy because we know x equals pi over 3. So this is the sine of pi over 3, right? This we're going to come back to, and then cosine pi over 3. So how are we going to get cosine of y and the sine of y? Well, let's go back to what we know. We don't know what y is, but we know its sine is 3/5. In other words, this implies the sine of y equals 3/5. And we also know sine inverse tells us that y either has to be in quadrant 1 or quadrant 4. There's no other possibility. Well, because 3/5 is positive, that tells us this is in quadrant 1. So we know y is here. Sine of y is 3/5, opposite over hypotenuse. Again, this is a 3, 4, 5 triangle then. 4 squared plus 3 squared is 5 squared. And because we can figure out this side, we now know cosine of y is 4/5. So we don't need to know what y is. We can use the triangle to figure it out. Cosine of y is 4/5. Sine of y, well, that's actually given right here, 3/5. So now we still need to evaluate sine of pi over 3 is the square root of 3 over 2 times 4/5. Cosine of pi over 3 is 1/2 times 3/5. So we get, and notice how these have common denominators again already, which makes the problem nicer to work with. So we get 4 square root of 3 over 10 plus 3/10. With that common denominator, we can just write that as one fraction. 3 plus 4 square root of 3 over 10. Now, this one you could check with the calculator because you have numbers in here. But again, the calculator value will be irrational, like a decimal number, right? This is irrational also, but it's a decimal number, non-terminating, non-repeating. So that's not the number I want on the exam. If you just put the decimal number down, you're not going to get any credit. You need to show that you can find the exact value. That's what it says right here. So this is what I'm looking for. All right, let's go on to the tangent identities then, sum and difference for those. So I've got the two formulas here. We're actually going to prove one of them because the proof actually uses the sine and cosine formulas, so it's kind of a fun one to do. It gives us another application of the sine and cosine formulas. All right, so what we do is we start with the left-hand side, tangent of x plus y. And we note that tangent is sine over cosine. So this will equal the sine of x plus y, over the cosine of x plus y. So like I said, we actually apply the sine and cosine formulas for addition, or for a sum. So this is sine x cosine y plus cosine x sine y over cosine x cosine y minus sine x sine y. So those are just our formulas. So now how you look at this and you compare it here, And you got to get from here to here. Maybe you want to stop the video and think about that and see if you can come up with it on your own. Notice that the plus and the minus is there, right? If you pay attention to the terms, you might be able to come up with something. So think about that for a little while, and then come back to the video. And hopefully when you come back, when you come back, you've come up with it. But now I'm just going to tell you. If you're looking at this, notice the one thing that stands out is you need a 1 here. So how could I get a 1 in this term? And of course what I would need to do is divide this by cosine x times cosine y. So that's what I'm going to try. I'm writing it over so far. 1 over cosine x cosine y. When I do this to the bottom, I have to take this times both of these terms, right? And whatever I do to the bottom, I need to do to the top as well. Before I write it in the top here in the numerator, I'm going to check though. So of course I'd get a 1 here. The question is, if I take this divided by this, do I get tangent x tangent y? And yes, I do. Sine x over cosine x is tangent x. Sine y over cosine y is tangent y. So that seems like the right thing to do. So I'm going to do it in the numerator as well. So when I distribute, I'm going to put this step in. All 4 of these terms get divided by cosine x cosine y. So in the numerator, we get this. Cosine x cosine y over cosine x cosine y plus cosine x sine y over cosine x cosine y, and over, move my equal sign, cosine x cosine y over cosine x cosine y minus sine x sine y over cosine x cosine y. We already talked about the denominator reducing to what we need, 1 minus tangent x tangent y. But what about the numerator? Well, notice sine x over cosine x is tangent x, and the cosine y's cancel. So we get what we wanted in the first term, plus, in the second term, the cosines cancel, sine y over cosine y is tangent y. And that's what we wanted. So we've proved the identity. So there's another example of using the sine and cosine formulas, this time to prove an identity. Well, so that proves the sum formula for tangent. The difference formula, the proof, you just use the difference formulas for sine and cosine instead. And notice the pattern, again, very similar, just the signs are different. So for the sum formula for tangent, the addition is on top and the subtraction is in the bottom, but it's the tangent x tangent y and then 1 minus tangent x times tangent y. Same pattern down here, just the signs in a different place. So we're going to just do one example using these formulas, but any of the previous problems that we did, we could do something similar for tangent too. And of course, like in this problem that we did, we could add tangent alpha plus beta to this and find that as well. Obviously, we'd need to find the tangent of beta. In addition to what we found before, but that'll be pretty easy to do. It's not too much extra work. All right, but we're just going to prove an identity. This type of formula is called a reduction formula. Where you have your angle plus or minus some shift in terms of pi. So this one is theta plus pi. It could be theta minus pi. It could be theta plus pi over 2. Of course, that would change what this equals, but you get the idea. Those are all called reduction formulas. So this one we're going to prove, and obviously we have a sum here, so we're going to use the sum formula for tangent. This is a pretty quick and easy proof. So tangent of theta plus pi would equal the tangent, of course we get a fraction here. So I want to move this up a little. Tangent of theta plus tangent of pi over 1 minus the tangent of theta times, the tangent of pi. That's multiplication. So tangent of theta obviously does not simplify. And then the tangent of pi is 0 over 1 minus tangent of theta times tangent of pi again is 0. So this term becomes 0, and we just get 1 in the denominator and tangent of theta in the numerator. So that just reduces to tangent of theta, and we've proven the identity. So that one's pretty easy to prove. The reduction formulas, you always use your sum and difference formulas to prove those, and they work out pretty nicely. You just need to be able to evaluate, whether it's a sine or, it could be a sine, cosine, or a tangent reduction formula. You have to just do the one evaluation, and they work out pretty nicely. Okay, so that's it for that section. Again, these sum and difference formulas, well, I can't remember saying again, but I can't remember if I said it or not. You don't have to memorize, you don't have to memorize these for the test. I will give you these on the exam. I'll talk more about that later. Okay.